Okay, welcome to example 2 on page 86 of the workbook. Okay, here we're continuing with section 2.8, and this time they're giving us a limit that looks more like the types of limits that we did earlier in the course. We would like to find the limit as x goes to 0 of sine of 2x over 3x. Okay, and they'd like us to first do that problem using a table of values. Okay, so we're gonna make a row with our x's and a row with our f of x, our function. Okay, and the question we're always asking ourselves when we use this table method is, what kinds of x values do we want to plug in here? Okay, well, that always comes down to what it is that x is approaching. In this case, x is getting close to 0, so we want to choose a list of x values that approach 0. All right, so partially up to you. Any list of numbers that gets closer to 0 will do. I'm just going to pick a few. So maybe start with 0.5 and then move on to 0.1, 0.01, 0.001. What's important again here is just that our numbers that we're choosing get close to 0. Okay, and one by one, we want to take those numbers and plug them into our function, okay, which in this case is sine of 2x over 3x. So let's start with the 0.5 and just do that calculation over here. Sine of 2 times 0.5 over 3 times 0.5. You can do this calculation on your calculator. Just make sure that you're in radians when you do it. That's important when we're using trig functions in a calculus class. Okay, and if you do that, what you should end up with it for an answer is 0.561 if we round it off. Okay, and then we'd move down the line, move over to 0.1, substitute that in, and you're going to get 0.662. Okay, and I'm going to go ahead and just show you what I got when I substituted these last two in. 0.667 and then 0.667. And the fact that those last two numbers repeated indicates that we're probably going to keep getting that number over and over again if we round off to 3 decimal places. Okay, so our best guess for the limit based on the table is that this limit appears to be about 0.667. Okay, so we've got an estimate of our limit to 3 decimal places, but then they ask us an interesting question. Is it possible to find the exact value of this limit? Okay, it turns out that there is, using a tool called L'Hopital's rule, which is new to us. Okay, and I'm going to just demonstrate to you kind of what that looks like. So the exact value of the limit. And let's first remind ourselves of how we approached this idea of finding an exact value for a limit earlier in the course. Okay, this has been a while, I know, but what we did way back when was we just tried to directly substitute in the x value that we're approaching. Okay, so if we did that, we would get sine of 2 times 0, which is sine of 0, over 3 times 0, which is 0. And what we'd discover is that this has the form 0 over 0. Okay, if you look way back in your notes, way back towards the beginning of the course, we called this an indeterminate form. Okay, in other words, if you get 0 over 0, further investigation is required. We can't tell whether this limit exists or doesn't exist. Okay, in other words, getting 0 over 0 doesn't help us to calculate the limit. It might exist, it might not exist. And so here's what L'Hopital's rule says. If you have a form like 0 over 0, what you can do is take the derivative of the top and the bottom of this function separately and try to calculate the limit again. Okay, let's walk through that together. So if we start with the numerator, you would first ask, what is the derivative of sine of 2x? Okay, well, that's a chain rule problem. We would get cosine of 2x times the derivative of 2x, which would put a times 2 at the end. Okay, and then what's the derivative of the bottom? Okay, the derivative of 3x is just 3. Okay, and we can now try to take this limit again, okay, by just substituting in x equals 0. So we're going to get cosine of 2 times 0 is 0 times 2 over 3. And then what is the cosine of 0? Well, you might remember that it's 1, or you could ask your calculator. And so we're going to get 1 times 2 over 3, which is 2/3. That turns out to be the exact value of this limit. And as a decimal, 2/3 is 0.6666 off to infinity. Notice that that agrees with the decimal up here that we got. Okay, so we are done with this problem. Let's talk about this L'Hopital's rule, okay, that we were talking about. That's what we really used right here. So we're going to describe that method in general, okay, on the next page. So let's scroll up here. Okay, and before we describe the rule, L'Hopital's rule is intended to help us with limits that are in what are known as an indeterminate form. Okay, 0 over 0 is the form that we just looked at together, but there are 4 others where L'Hopital's rule might help us. Okay, various combinations of plus or minus infinity over plus or minus infinity. We can also use L'Hopital's rule in those situations. Okay, so here's what L'Hopital's rule says. Okay, it basically says that if we have one of the indeterminate forms listed above, then we can calculate this limit by simply taking the derivative of the top and the bottom, notice the f prime of x and the g prime of x, and just repeating the limit and hoping that by taking that derivative, we've turned our limit into something that we can more easily calculate. And okay, that's the idea. Okay, we're going to do a number of examples involving that. I do want to make a couple of comments first. Okay, and we'll see this in the examples that we do. First of all, it's very important to realize that if you want to use L'Hopital's rule, then you have to be in one of these indeterminate forms. Okay, our limit has to look like one of these 5 forms up here in order for this rule to work for us. Okay, and the second one is just a comment about some other types of indeterminate forms. 0 times infinity, 0 times negative infinity, those are situations where we can also use L'Hopital's rule. Those types of problems are a little bit different. So depending on how much time we have, we may actually look at a couple of that.